So today we will start the other chapter, which is also a separation technique based on the same principle, which is the difference in the boiling point of the mixtures. Now, what we did last time was to develop the equations or study the model that will explain or describe the separation of two components using distillation, but for one stage only. So we only discussed one stage distillation or separation. Today we'll extend our approach or our method to include more than one stage, which is called distillation. Distillation, typical distillation, of course, but at least we'll give you some idea of how you can come up with the equations. And again, the equations are similar, material balance equations and equilibrium equations. And that's it, and then the constraint. But now, instead of having only one stage, we will be having more than one stage, 3, 2, 4, depends. So what we're going to learn from this topics or from this chapter basically is explain the need in distillation for a condenser. When you look at any typical distillation column, you will see there is a condenser at the top, and there is a reboiler at the bottom of any distillation column. We will see what is the principle of why we need this condenser to produce the reflux, and why we have reflux, in fact, and why we need the reboiler at the bottom of the column to produce or to generate the boil up. Now let me draw this distillation column, typical distillation column. We will explain it in more details, but usually this is the figure that you probably see in any typical distillation equipment. Usually this is your cooler or condenser. So we use sometimes cooling water, will depend on the temperature, of course. Here we usually use steam to generate heat, so we can generate this vapor that is going to go back to the column, and this one is also going to go back to the column. The liquid here, which is going to be called the reflux, is going to flow from the top of the column and then goes down. The vapor generated at the bottom here is going to move toward the top of the column. Now this is the minimum configuration, or this is the typical configuration of any distillation column. You probably see some other more advanced distillation columns, and where we have more than one condenser and more than one boiler, and these are called, in some cases, intercoolers or interboilers. But of course, the purpose of these several intercoolers or similar, let's call them steam generators, are the same principle. We will see why we need these two. Again, for a binary system, we will be able to determine the 5 construction lines of the McCabe-Thiele method using material balance and vapor-liquid equilibrium relationship. So as I said, we're going to solve the distillation column model using, again, material balance equations and equilibrium relationships. But we will learn how to do that graphically. And the graphical approach is usually called McCabe-Thiele method. You remember the graphical approach we used when we solved one stage binary distillation system, which is called flash, and we end up with the graphical solution. The graphical solution for distillation, where we have more than one stage and we have only 2 components, is called McCabe-Thiele method. We'll explain that, how we construct this one, how do we know the number of stages based on this graph. And then we will explain the effect of feed, how the feed conditions. When we say the condition of the feed, we mean by whether it is liquid or vapor, whether it is saturated liquid or saturated vapor, or superheated or subcooled mixture. and if it is a mixture, so how this will affect the number of stages. Apply the McCaptail method to obtain the minimum reflux ratio, minimum equilibrium state, and number of stages for specified reflux ratio greater than minimum. So once we explain the idea and the structure of the graph, which is called McCaptail method, we will see how can we use this to determine the limitations. And this is a very important step when you do any design in the future, inshallah. Whether you will be using software or anything, you should know the minimum reflux ratio and the minimum equilibrium stages, since these are two parameters that you should provide the software in order to calculate or in order to solve the model. So you want to be able to know where you are exactly, so you don't specify a number of stages which is below the minimum number of stages, or you don't want to specify a reflux ratio below the minimum reflux ratio. Otherwise, you might not get any conversion, and the program will run forever without getting any solution. And in some cases, the only reason why the software is not converging because you have one of these numbers beyond the limitation. That means either you specified by mistake the number of stages below the minimum number of stages, or you specify the minimum reflux ratio or the reflux ratio that you want to work on below the minimum reflux ratio. So you wanted to know how to determine these two parameters. So you wanted to avoid working beyond this frame or beyond this zone. We will also explain the principle or the definitions of the stage efficiency. And most of the time, we will be assuming the stage efficiency to be 100%. Now, we would like to know what is the meaning of the stage efficiency to be 100%. It means the vapor and the liquid had enough time to be in equilibrium. So, but in reality, it is not the case. In reality, the equilibrium stage that you're going to model, as we will see, inshallah, it's not at equilibrium, or the vapor and the liquid in that stage are not at equilibrium. The boiler, yes, the boiler is considered to be equilibrium stage because the conditions are, or the conditions of the boiler meet the requirement for this stage to be at equilibrium, or for the vapor coming out of the boiler and the liquid leaving the boiler are two at equilibrium. But for the stages, it is not. We will see how can we include this effect, or how can we sort of count for this deviation from the equilibrium using Murphy vapor stage efficiency, what's called Murphy efficiency, and how the number of stages that we wanted to calculate will be different. Now, we probably, I will see if this is possible or not, we might cover part of this one, which is going to be including or how do we apply McCaptail method if we have multiple feeds and side streams and open steam in place of reboiler. These are very common, multiple feeds and multiple streams and open steam. It means instead of using a reboiler, you will be using steam instead of that. How this will affect the way how we calculate the number of stages. Okay. So we'll start with distillation. Now, what is distillation? التقطير بمعنى اللغة العربية هو عملية التقطير أو عملية الفصل, the way or the operation of separation, or the separation process based on the difference in the in composition between liquid mixture and vapor formed due to the difference in the volatility. You remember, volatility is function of what? Function of boiling point. So the distillation is a way of separating two components or multi-component system, and the separation is based on the difference in the volatility. Why they have a difference in the volatility? Because they have difference in the boiling point. If the components in your system have similar boiling points, then this distillation or the separation by distillation will not be effective. So you will have to find out another approach to separate the components from each other. So the idea here, or the thing that you want to keep in mind, your mixture that you wanted to separate must have, the component in the mixture must have different boiling points, and there must be, let's say, significant difference. If they are very close, separation is not going to be possible. Or, as we will see, the number of stages will be too many, sorry. It depends on the distribution of the components between the vapor and the liquid phase, which is also referring back to the, if you remember, the Ki is equal to Yi over Xi. So that must be huge, or at least not equal 1. If you have this one equal 1, that means the mole fraction in the vapor phase and the mole fraction in the liquid phase. So that component will be the same. This is not what you want. In fact, you want something in the vapor higher than in the liquid, or the other way around. Or maybe for heavy components, you want to have Xi to be greater than Yi for any separation to take place. Otherwise, if you're going to have a component here in that mixture, for example, and this is your distillation, and then you have your product here, and this is for, let's say, for example, this is your vapor, and this is your liquid, and this is your component I going here, and there is a mole fraction here, and X mole fraction of that component. If the Xi and Yi are the same, so there is no point of installing this equipment, and at the end of the day, the composition is the same. The composition of the vapor formed as a result of vaporization must be different from that of liquid. This is what we just said here. This is something you can see. Just a moment, let me take off this. You remember this diagram, which is TXY diagram. This is the saturated line or bubble point line curve. This is the saturated vapor line curve. So this one, we can say this one is basically T versus Y, and this is T versus X, and this is for binary system, by the way. Let's say you have a feed that has 50% of component A, let's call it 1 or A if you like, and 50% of component B. If you heat that system, you will have Y at, it's going to be 0.7. Okay, see here. If you heat it up here a little bit, you make a mixture at this point. So if you heat it a little bit up to this point here, let's say 96, maybe something like that, and you will end up having two mixtures. The vapor will contain 60%, and the liquid will contain 37, or let's say 40% of component. And this is not B, we're not referring to B, this is the composition, or let's call it mole fraction of the more volatile component and the bottom product. So in some textbook, they use B to refer to the bottom product, and some textbook, they will refer to the bottom product to be W, so you have to be careful. And this one usually referred to as D, because they wanted to call it distillate. So this is the mole fraction of the more volatile component, and let's call it in the top of product. Sometimes they call it distillate. Usually call it distillate if you are talking about a distillation column, and the top distillate product. So want you to see that because of this distribution fact of the more volatile component, if you heat that system, which is containing 50% of component A, and you introduce it to a flash drum, you will end up with two different mixtures. One will be having 60%, the other one will be having 40% almost. Now, there is no relationship between this one. What is the relationship between XB and XD here? Can you tell me what is the relationship here? Do you know what is the relationship between XB and XD? XB and YD? Any idea? Do you know why XB, what's the relationship between XB and XD? The relationship is they both are at equilibrium. So here, at equilibrium. So XB and YD, or let's call them the mole fraction in the top product and the mole fraction in the bottom product for one stage, are at equilibrium. So it's basically you have a mixture here in which you have Z is equal Z1, 0.5, then you will end up with two vapor and liquid. YD here would be at 0.6, and XB, let's call it 0.37. The YD and XD, as you see here, at equilibrium. Now the idea from this is to, instead of having, now you want to do what? You want to increase the composition from 0.5 to, let's say, 0.9. So you want it to come to some stage here. So you have to add more stages. So what you are doing here when you're going to move to the right, you have to cool. So, and at the same time, you wanted to obtain XB, or your composition here will be very small, let's say here. So you want to reach to this stage. So on the other side, you want to cool, you want to heat, you add heat from stage to stage. So these are the stages that we wanted to design. Okay, these are the number of stages that we wanted to calculate. This is the distillation. So the distillation is to add more stages to increase the purity from, instead of only 0.6, you want it to reach, let's say, 0.9, for example. At the same time, you wanted to reduce the composition and the bottom product to be 0.05. So you want, instead of 0.37, you want it to be around this number. So you have to go up. When you want to go up, you have to increase the temperature. How we increase the temperature? We have to add the heat. We have to heat the system from stage to stage. Every stage you have to heat. So, and that's why we need, so we have cooling here taking place, and we have heating taking place. The cooling will be done, all of the cooling needed in the distillation column will be done by the condenser. So you remember why we need a condenser? We need to do the cooling because we want to obtain high purity product. And the heating will be done using the reboiler at the bottom. All of the heating required for all stages will be provided by the reboiler. Okay. So distillation of the binary system, we have different approaches or different mechanisms by which we can do distillation. We have one called batch distillation, which is called differential distillation. We will discuss that later on, I think, in chapter 13. Unsteady state, of course, batch distillation, where we have the mixture, the feed. You start at time 0, and you load your feed. It's called feed 0 is equal, let's say, 100 mole, and x0, let's say 0.5, and then you install something to condense it here, the product, using the cooler. And then you start adding heat, Q, and then you keep adding heat, so there will be vapor forming here. And after some time, you will find your feed you started with is decreased. The composition of the more volatile component here will increase, so you will end up with two different products here. One is going to be called the residual, and one is going to be called the distillate. And this is the batch distillation. We have a continuous distillation. This is what we're going to discuss, inshallah. Flash distillation and rectification. Flash distillation and rectification. Rectification is the continuous. We have more than flash distillation. We already discussed. When you have one stage, then you can have two products. One is going to be the vapor phase, and one is going to be the liquid phase. And we develop the equations, and we know how to do that. For the rectification, which is something we're going to discuss, inshallah, now, where we have a distillation column that is going to be used to install more than one stage. So you're going to have more than one stage. You have your feed going into somewhere in the middle, depending on the composition and the condition of the feed, and then you're going to have condenser, as we said here, and you're going to have product here, and you will have a reboiler where you're going to add steam here, and you're going to cooling water, and this is steam, and this is your product. You call it W or B or whatever you want to call it, and this is usually called D because it's distillate, and the composition here is called YD, or you can call it XD. Here they call it XP or XW, both are okay. And this is your feed going into the system, and the composition is called ZF or حتى XF, it's fine. And here are the stages that you need to do or to perform the separation required to obtain this YD and this XW. Now you are constrained, so you have constraints, and one of them is the material balance. You have to ensure the material balance is okay. And also the equilibrium stages, it's going to be assumed to be equilibrium stages. And for each stage, you're going to have Ki, which is K1 and K2 for binary system, for each stage. So for each stage, because you're going to have different K values since there are different temperatures. But as I said here, the heating required to increase the composition of the heavy component is going to be supplied by a reboiler, and the cooling required to increase the more volatile component, mole fraction in the D product here, is going to be provided by the condenser. And now our design or our sizing, let's call it, it's not design, is going to be determining the number of stages needed for any specific distillation column. So, any questions so far?
No. Clear.
Okay, so this is the distillation column that we will be working on. This is typical one. I got it. I stole it from the net, but it seems to me like it's very clear. Yeah. It has all the names we're going to deal with. You see here there is a reflux that we're going to need. Of course, don't worry about these valves. They are control valves, but don't worry about them. But I want you to know there is three, let's call it equipment minimum. Three equipment. The first one called distillation column. Sorry, this the equipment that carries the trays here, and we have the condenser that will be used to absorb heat or to remove heat, cooling. So as you can see here, there's vapor here going up. We need to condense some of that vapor, and then instead of having all the vapor as a product, we will using part of this product here, so to return it back. Okay, and the bottom section, which is as you can see, there's a liquid here going out, and we're going to use part of this liquid to generate the vapor that we need. Now the vapor here produced is called boil up, and this one is called reflux. Okay. Now as you will see here, for each stage we have vapor going up and liquid going down. And as I said before, we're assuming the liquid leaving. So if we have this stage, let's say, and you're going to have, this is vapor going up, this is stage N, let's say, this is stage number N. You're going to have vapor going up, and the composition of that vapor is going to be Y. And now Y, YN or XN, we are referring to, يعني احنا نقصد به هو the composition of the more volatile component. So we still, whenever we mention molar fraction, we are referring to the more volatile component or the light component. And also here there's liquid going down, so we call this one Ln, and the composition of the more volatile component will be Xn. So in our design, or in this at least study, or in this investigation, we will assume both are at equilibrium. And we will assume the stage is at equilibrium stage, or we assume that these stages are equilibrium. As I said, this is not valid. It is not valid, but it is not true. In reality, you have to take into account that Yn and Xn are not at equilibrium. Okay. In most of the cases, the condenser usually is total condenser. When you hear someone telling you the condenser is total condenser, it means all the vapor will be condensed. So all this vapor will be condensed. Now, is this all the time the case? No. It will depend on the mixture you are dealing with. Now, in most cases, for example, if you go to the gas industry, where we have very light components like C1, C2, C3, you will not see a total condenser. You will see a partial condenser, and the condenser will look like this one. See here, this is your, let's say, stages, and then here you're going to have the condenser like this one. So you will have partial condenser. So you're going to have vapor product and liquid product, liquid retain. So this is their flux. So as you can see, if you compare this one with this one, you will see the product is liquid as well here, so, because this is what we're going to produce since we condensed all of the vapor coming out of this, of the top of the column. But this is because we are able to do that since the components are easily condensed. We don't require that much of cooling. But if you are dealing with light components here, you will not be, not technically, but pragmatically, practically, it's not wise, because it will cost you too much money in order to condense all of the vapor here, since you have very light components such C1 and C2. So the total condensation will cost you too much, and usually we will produce vapor. So the product will be a vapor instead of liquid. So we will see how we're going to deal with that one. Okay, so just to remember, you can have both cases in your design. The feed now is also will be going somewhere in the middle of the column, but which stage must be introduced to? So where exactly we have to introduce the feed. Put it in here or here or here. So you got lots of options here. So this is one of the things that you're going to determine. You will determine which is the optimum feed stage, where exactly we have to put, or where exactly we have to introduce the feed. The second thing is to determine the number of stages needed for this separation. Now, what about the QC and the Q? Of course, also you're going to determine, or it's going to be given to you, the composition of distillate and the composition of the bottom product plus the flow rate of D, the flow rate of B. So these are the things that you're going to determine, or it must be given to you to determine the number of stages. So basically, the composition of the feed will be given, and the flow rate of the feed will be given, and then you will determine. Sometimes you will determine the flow rate D and B and the composition and the number of stages. And then you will be given the reflux ratio. Let's call it the flux ratio or the reflux rate. We have two types of reflux. We have external reflux, which is R over D, and we have internal reflux, which is the ratio between the vapor and the liquid in each stage. Okay, so this is V and this is L. Okay, this is Ln, the liquid going from this in. Let me take this one here. Why? So if this is going to be your stage number N, this is Vn, and this is going down. This is Ln because liquid going down, and the ratio between the liquid and the vapor is called the internal reflux, and the ratio between this one, let's call it L0, and the L0 over D is called external reflux. Okay, we will go through this one, inshallah. So a second phase be formed so that both liquid and vapor are present and can make contact while flowing counter to each other in a trade or packet column. So by the way, there might be distillation columns in which we have, instead of trade, we have packet, but we don't really discuss this in this course. But there is a possibility that you see distillation column in which we don't have trays, we have what's called packing. Now, the purpose of the existing of the two phases in each stage is to ensure we have mass transfer. When you have liquid phase going down and vapor phase going up, you want to move the light component from the liquid phase to the vapor phase, because you want to enrich the vapor which is going up with components. So there is mass transfer from the liquid phase to the vapor phase, which is going to be component A, to be transferred, the more volatile component, from the liquid phase, which is going down, to the vapor phase. So by this, you will increase the composition or the concentration of your component A in the vapor which is going up. And that's why at the end, at last stage, you will have a stream of high concentration of component A. But is this going to be possible if we don't, of the two phases are not in contact? So we have to ensure there is contact between the vapor and liquid phases. And there, first of all, we have to ensure we have liquid and vapor phases. If you don't have liquid and vapor phases, that means there is no mass transfer. And the basic idea of the separation is the mass transfer of the component, of the more volatile component from the liquid to the vapor phase, and the mass transfer of the heavy component, which is component B, from the vapor phase to the liquid phase. Now, is this something, it reminds you of something? If you have two components, A is going to in this direction and B is going in this direction. So this is in B, component B, and this is in A. And this is, let's call it the liquid phase, and this is the vapor phase. What is this mass transfer called? What we call this one? Do you remember?
Diffusion.
Yeah, what's the diffusion, the term that you used? We call
Mass
it
transfer coefficient.
counter current, huh? Counter current diffusion, where we have Na is equal to minus Nb, because for this to happen, you have to, whatever moles of component A going from this point to this point, because you have a mass transfer concentrate, you have to keep the same mass transfer. So you have to keep the mass balance there. You will have the same component of the same flow rate of B going from the liquid, from the vapor to the liquid. So this is what you will see, what we call it counter current diffusion. One is going this direction, and the other one is going in the opposite direction with the same flow rate. And this is something you already know in mass and separation course 1, I think. So we have to make sure we have liquid, two phases, and also we want to make sure they can be meeting. They will have to be meeting during this, uh, within this column. So the meeting, if it is happening stage-wise, if they are meeting only at some stages, we call it a stage column or trade columns. But in some cases, we can ensure or we can make the meeting continuous. And this is called packet column. In packet column, the vapor and the liquid will be having the chance to meet together continuously from the bottom to the top. And this is also, there are a few equations that you have to study in order to design. In packet column, what we calculate the length or the height of the packing. How much, let's say, how much the height of this packing to be there for this separation to achieve the requirement that we want in this separation column. In the distillation column, which works based on trade columns, we calculate how many trays we need to achieve the required separation in this process. But for both cases or for both designs, the idea is based on the distillation, which is based on the difference in the boiling point and based on the equilibrium constant or the distribution coefficient between these two components. Okay, so we have to, and this is another reason why we have to ensure we have some liquid going back here, because if there's no liquid going back, that means whatever stage here will not be useful. Why? Because that vapor going up here will not have chance to meet with any liquid. So that means it's like you have only one stage. And also for this liquid which is going down, if it doesn't meet up with some vapor from the other direction, that means that liquid going down, the composition of that liquid will not change. And this is not what you are trying to design. You're trying to design something that will, as you go down, the composition will decrease of the more volatile component. How that's going to happen? Uh, it's going to happen when you have some of the component A will go transfer to the vapor which is going up here. But if that vapor is not there, so the liquid stream will continue without any exchange of moles of component of the more volatile component with another, with any other phase, which means there will be no change in the composition. That means that's just the addition of a stage without any mass transfer or without any extra separation. Is this clear? So if I ask you why we need vapor, or let's say why we need the condenser and the boiler, we need the boiler and the condenser to provide the liquid and the vapor for the separation, and also to ensure we remove the heat required for the cooling, and we add the heat for the heating needed in the distillation. Okay, any questions? So far, so good. Okay, so as you can see, components have different volatilities. We say that ready. We say this one, so that the partition between phases to different extents. So this is the same thing we discussed before. The two phases are separable by gravity or mechanical means. So the mechanism how this is going to work, you have the feed going up into the column somewhere in the middle of the column, and we said we're going to determine the optimum. This is one of the parameters that you're going to determine in the design of the distillation column, is to obtain or determine the optimum feed stage, where exactly your feed is supposed to be. Is it going to be in stage 1 or stage 2 or stage 3? So you see here, the vapor and the liquids are meeting in different stages, and that's why we call it what? We call it trade column. This is trade. You can say here trade, because I don't want you to see the textbook explaining, for example, a continuous contact. We call it continuous contact. Then it's basically different equations that you have to use. And there is some criteria by which you can design these trays here. So the liquid coming from the top is going to go down here, and then once it is going to move this direction, there will be some vapor going up here, and these trays are perforated. There will be some holes here that will allow the vapor to go up here, and while he's going up, it's going to be meeting with the liquid. So you see the bubbles of the gas or the vapor, and this is where exactly the mass transfer will take place. So here you have the component, more volatile component, will go from the liquid and will travel with the vapor, not all of that, but at least part of it. And then the liquid go, and again, there will be some transfer here between this vapor and the liquid in that stage, and this mass transfer will continue down to the bottom of the column. Last stage, or the last the bottom product, we'll have liquid here. We need vapor. That vapor we need it, so we have to heat the mixture to produce the vapor going up here. So we keep the same mechanism where we have vapor and liquid in the column. Again, the vapor, the last point here at the top of the column, there will be vapor. And if we don't condense part of this vapor and try to form liquid to go down, to ensure we have this amount of liquid going down, there will be no mass transfer as we explained, and that's why we have the condenser here, or the drum here. This is the condensation taking place in the condenser. You're cooling water, or it depends on the type of mixture you have. In some cases, you want to cool with water. In some cases, you need the refrigerant. In some other cases, you might be able to do this job by even fan. Fan means you're going to use the air for cooling. It depends. It depends on the temperature here you have in the column. And then once you have the liquid formed here, you take part of that and you put it back here to the column. So you keep the mass transfer taking place, and part of that is going to be going down. So this R of flux ratio is called L0 over D. This is called the external reflux ratio. For each stage, for example, the L over V, the quantity of L here going down to the V going up, is called internal refluxation. We'll explain that when we develop the equations. Feed is liquid, it flows down to a CV tray. CV tray perforated. I don't want you to focus too much on the type of the stage, because whether it's a CV bubble pack or bubble cap, or other types, because it is something we need when we do the rating, or when we're going to do the mechanical design, or if we're going to investigate the hydrodynamics of the column, which is not really covered in this course. It's something you're going to, inshallah, study in equipment design course. But regardless of the type of the stage, this stage character must be enough to allow for the contact between the vapor and liquid, and the design of that stage must also allow for smooth transfer or smooth movement of the gas bubbles through that stage without splashing and without flooding. All of these terms you will hear when you design this column and when you do the sizing and mechanical design, you will, inshallah, learn what we mean by this flooding and weeping and lots of phenomena that can happen during the separation you want to avoid. And these are functions of the flow rate, the diameter of the column, and the type of the stage used. But I don't want you to really focus on this one. Vapor enters the tray and bubbles through the liquid on this tray as the entering liquid flows across. So this is what we said. We are going to have in each stage bubbles of the vapor goes within the liquid itself, and then at this time there will be mass transfer taking place between the vapor and the liquid in that station. Now, the vapor and liquid leaving the tray are essentially, we assume they are at equilibrium. So, and at each stage, we will assume the vapor and the liquid leaving that stage will be at equilibrium. Okay, so as you can see here, the liquid leaving here and the vapor going up, we assume at equilibrium. Okay. Now, because of this assumption, that assumption will give us, will allow us to develop our equations, or at least to solve our equations, or at least to relate, if we call this one stage number n, so that will be yn, and that will be xn. And since xn and yn are at equilibrium, we can assume now k is equal to yn over xn. So we can use this relationship in our solution. This is the whole idea about that. The vapor continues up to the next tray or stage where it is again contacted with downflowing liquid. So this multi-contacts or contacting will be continuing from stage to another stage and so on until it reaches the top. The concentration of the more volatile component is being increased in the vapor form, each stage going upward, and decrease in the liquid from each stage going downward. So while you are having this component, more volatile component moving or transferring in each stage from the liquid to the vapor, what you will see as you go down, the composition of the more volatile component in the liquid phase will be decreasing, يتناقص, and the composition or the mole fraction of the more volatile component in the vapor phase will increase until you reach the last stage at the top. So you will end up with two streams. One is going up and one is going down. The last stage at the top will contain a huge amount of the more volatile component, and at the bottom, liquid at the bottom will contain less amount, or let's say very minute amount, very small amount of the more volatile component. And the other way around for the heavy component. The heavy component will be more concentrated in the bottom product because it's going to move from the vapor to the liquid as we go down, and also will be very small, more fraction of component, heavy component in the top product. And this is what we are looking for. It's going to be to separate the heavy component from the more volatile component. The more volatile component will go up and the heavy component will go down. Why this one going up and why this one is going down? Because the distribution, because of the volatility, okay, or let's call it because of the boiling point. Yes, go ahead, Bushra.
And sir, what is exactly the use of and importance of the external reflex ratio?
Not the reflex ratio. This is a parameter, but maybe your question is why we need this reflex. Is that your question?
Yes.
Yeah, because we said we need this reflex because we wanted to make sure we have liquid that is going to be, if we don't have this reflux, if we assume if that's the case, let's say let's take this one off here, okay? Let's assume we don't have this reflux. That means we have this, the top of the column here, and we have this product. Okay, is that what you mean? Now this is my product. Now here we have stage here. Huh? This is another stage. Now we have vapor going up here, and at each stage we need the vapor and the liquid. Now where are we going to get the liquid from? If there is no liquid going back, where are we going to get this liquid here? Because this is the liquid at each stage. So we don't have liquid. That means all of these stages are useless, because the vapor will not find any liquid here, will not find the liquid here. So the composition of that component here, Y component here, let's say this is stage method, for example, 3 and 2 here. The composition of the more volatile component in this stage and in this stage, all the same, there's no change. Why? Because there's no mass transfer. Why there's no mass transfer? Because there's no another phase. We have to keep two phases throughout the column. And we can do that only by taking part of this and condense it here and return it back, so we can ensure we have liquid here. And we have liquid at each stage. And this is also for the vapor. If we're going to, if we have a vapor like this one, okay, and this is our product gone. This is my product here. Now I have stages here, huh? And the liquid is going down here. This is the liquids. And try looking for vapor to contact, because for mass transfer we have vapor, but we don't have any vapor. So the liquid is going from one stage to another stage, and there is no contact between the liquid and the vapor, because there's no vapor here. That means we don't have any mass transfer, and all of these stages you are installing is going to cost you money, but there's no any useful, they are not useful for the separation that you're trying to do. So we need the reflux and we need the vapor to ensure I have vapor going up and liquid going down at each stage. Is this clear? So remember, for distillation, we need to have, for distillation columns, we need to have reflux and we need to have vapor. Now, you can see some of the distillation columns, you don't have reflux, but you have the feed going from the top. Instead of going in the middle, maybe your feed is going to be introduced from the top. Okay. Now, I will take you back to course separation 1. Did you study absorption?
Yes.
So what was the two phases that are contacting each other in the absorption?
Liquid and vapor.
No, not liquid and vapor.
Solid and the gas?
Gas, not like vapor. It's a very big difference between gas and vapor. And the contact on the design was simply, you have this one, trays also. You have the vapor, the gas going from the bottom and leave the top of the column. You have the liquid going from the top, leaving. So you have this one, L0 and Ln, if you have the same nomenclatures here. And we have V or G N plus 1, and you got G1, because this is 1 and 2, and this is your N number of stages. Now here there is contact between the liquid and the gas in each stage, huh? Do we have reflux here? Do we have reflux in the absorption?
No.
No, why? Because I kept the vapor going from the bottom and the liquid going from the top. So I'm ensuring here we have liquid and vapor in this stage, liquid and liquid and gas in each stage without introducing any reboiler or any condenser, because the liquid is going to be continuously introduced from the top, and the vapor is going to be the gas, sorry, is going to be continuously introduced from the bottom of the column. So mass transfer is going to take place also in the absorption, and the and the relationship between these two are related by what? What is the relationship between, let's say, the vapor composition and the liquid composition here? What is the data here? What did you call the data here? In distillation, we call them equilibrium data. What do you call these ones in the absorption? Do you remember? What is the type of the data there? Is it the same? Guys, wake up. Do you know what is the type of this data? When you go and solve the absorption problem, what is the data? What is the equilibrium data? Where do you get it from? Now, the equilibrium data, or the absorption, is taking place at isothermals. Huh? It's happening at the same temperature and the same almost pressure. But distillation, no. Distillation, we have different temperatures. Huh? Each stage will have different temperature. So where we get the data in the absorption system? What we call this kind of data here? Do you remember? Have you ever used any equilibrium data in absorption, design of absorption column?
No.
No, really. So how did you design? Have you ever designed any absorption column? Did you calculate the number of stages? So do you know when we have to use distillation or we use absorption? Okay, so absorption, the data we use in the absorption problems, we call it solubility data. We call it what? Solubility data. In the distillation column, we call it equilibrium data. And that's why in distillation, we call all the time, we use this term vapor liquid equilibrium. In the absorption, we call it gas vapor equilibrium, because you have one component in absorption, you have one component which is going to be distributed between the liquid and the gas. And as you remember, hopefully you remember, in absorption we have the solvent, we use it usually. So the solvent is not going to be moving to the gas phase. And the component that you wanted to extract or remove from the gas phase is going to have the ability to travel without moving any other component with him from the from the gas to the liquid. And that's what we call it solubility data. And usually we can use Henry's constant, if you remember. Okay, so please remember and try to learn. And absorption is also another important operation that you will design when you start working in real time. So the first thing you want to know, when should we use absorption and when should we use distillation? Okay, and the absorption is not a function of the boiling point. It's function of the solubility. But distillation is basically function of the difference in the boiling point of the mixture. Okay. Okay. This is the final vapor product coming overhead is condensed in a condenser and a partial. That's what we call it. The product we usually call it distillate here is removed, which contains a high concentration of A. Now A is referring to the more volatile component all the time. The remaining liquid from the condenser is returned back. This is part of this product. We have to return it back to keep liquid flowing down in the column, and it's called reflux. The liquid leaving the bottom trays, this one, into the boiler where it partially vaporized. So don't vaporize all this liquid. We partially vaporize this one just to ensure we have enough sufficient vapor going through the column toward the top of stages. The vapor from the boiler is sent back to the bottom stage, tastes much greater anyway. Now we will start, any questions before we start developing the equations? Okay, so now what we will do, we try to explain the McCabe-Tail method, which is, as I mentioned before, it is a graphical approach to determine the number of stages. So all what we're trying to do right now is to calculate how many theoretical stages that we will need for specific separation problem. For binary system, again, we are talking about binary system. So number of theoretical stages. Why we call them theoretical stages? Because we assume these stages are at equilibrium. As we said, they are not, but we assume at equilibrium, so we call them theoretical stages. So a mathematical graphical method, so this is trying to explain McCabe-Tail method. It's very famous, and it is still studied and taught by all in all courses, because it's very important, and it's really very useful to explain the principles and the idea of the distillation. So it's a graphical method for determining the number of theoretical trays or stages needed for a given separation of binary. So it is only for binary system of A and B. Now, of course, A is going to be the more volatile component. B is going to be the heavy components, has been developed by McCabe and Tail. These two guys, and why we usually have these kind of approaches, because they are developed long time ago, before the computer was really in place, and that was impossible for anyone to do the calculations by hand. Then if you want to do the calculations by hand, it is technically speaking, okay, you can do it, but it will require lots of time, especially if you have, for example, 30 or 40 stages, then it's going to be very tedious, and especially without the computer, it will become, it's almost impossible. So that's why they try to develop this method. It's, of course, an approximate method, would give you some approximate results, but it's pretty useful, especially for preliminary studies. The method uses material balances around certain parts of the tower. So in this approach, we divide the tower into different sections. We have at the top section above the feed stage. So for example, as we mentioned here, we have feed stage and we have condenser here. And the boiler here, this is your feed. So the method tried to deal with this one alone and determine the number of stages at the top or above the feed. And he will deal with this one alone. And then he will combine the two sections altogether. And he also will tackle the feed location alone. So he's trying to divide the column into different sections. And then finally, he will combine all of these. And the equations used for each section will be used to determine the, what we call it, the material balance line, which is operating line, plus the equilibrium line, since we know they are at equilibrium. And from this, we will be able to determine the number of stages for each section. Okay. So the method uses material balance around, which gives the operating line. So the material balance for each section will give me the operating line. We will know what is the operating line. And the XY equilibrium curve for the system. So you'll end up with two curves. You have XY curve, which is basically something like this one. This is the equilibrium curve. This is X, this is Y, and this is X. This is the equilibrium curve. We know it. So we will see how the operating line will be drawn within this curve or within this graph, and how it is going to be looking like compared to the equilibrium line, and how from this line and from the equilibrium line, how we're going to be able to determine the number of stages. So this is the story. The whole story is how to determine all of that. So before we start explaining the equations, we will see that there is some assumptions that you have to remember. Main assumptions: equimolar overflow through the tower between the feed inlet and the top tree, and the feed inlet and the bottom tree. So when we explain it, that this is the feed. We said these are the trays. Let's call them trays like this one. So you have in each stage there's this one going down and this is going up. So let's say this is M, and this is also, there is this one and this one here. This is N. So we want to call, we want to mention the stage, in a stage at the top to be N. Maybe that one, N 1, 2, 3. We will use N if it is, this stage is above the feed, and will be M if it is below the feed. It's just to choose these two. Maybe you wanted to flip this one around. That's fine. So the liquid which is leaving that stage will be called Ln, and the vapor is going to be Vn. Again here, Vm and Ln. Lm here. So this assumption says that liquid in each stage at the bottom will be almost the same. The flow rate will not be changing that much, which is in fact is changing. But here, this analysis, McCabe said this is going to be assumed to be constant. It doesn't change that much. And also the vapor here, so Vm, sorry, Vm minus 1 and Vm minus 2 is equal to Vm. So the vapor flow in the bottom section and the liquid flow rate in the bottom section are constant, but they are not the same as the vapor flow rate at the top and the liquid flow rate at the top. Okay. The other assumption is liquid and vapor streams enter tray are equilibrated and leave. So we assume the efficiency to be 100%. So these are the two main assumptions that you will have to remember. Or if you are asked what are the main assumptions used to develop the McCabe-Tail method, we have to say we assume the molar flow rate is constant from stage to stage, doesn't change that much for both liquid and vapor, and also the equilibrium, and the stages or the efficiency of the stages are 100%. When we say the efficiency, we mean the stages are at equilibrium. It's an assumption, and we will correct this assumption later on when we calculate the number of theoretical actual stages. We will have to divide by the number of this efficiency number. Is this okay, guys? So far, so good?
Doctor?
Yes?
In real life, is it possible to have 100% efficiency of the tray?
No. Anyone tells you that, he is lying. The tray efficiency will never be 100%. The only stage that we can assume 100% is the reboiler. Reboiler is not assumptions. Reboiler is a fact that the liquid leaving that reboiler and the vapor leaving that reboiler are at equilibrium. It's a fact. It's not an assumption. But for the other stages, it's not. The other stages are assumptions. And all the time you'll have to count for this. When you're going to do the real design, you'll have to divide by the efficiency. So if you calculated the theoretical stages to be, let's say, 25 and then you'll have to divide by the efficiency, which is maybe 40%, 60%, 70%, depends. Okay, divide, then you can calculate the actual number of stages needed. Now, maybe you will ask how we determine the efficiency. Determining the efficiency is going to be based on some correlations. It's very similar to the correlations that you have studied in heat transfer when you determine the overall heat transfer coefficient, if you remember. You know what is the overall heat transfer coefficient?
The U?
Yeah, this is the overall transfer. When you design the heat transfer equipment, you have something called heat transfer. And for any heat transfer, you have sometimes a loss of resistance between this point and this point. And all of these resistance are measured together and represented by what's called overall heat transfer coefficient. This is only because we want to simplify the calculations. And if you remember, when you designed the heat transfer equipment, such as, for example, tube and chill heat exchanger, you went through some of the charts where you can get some estimate for this heat transfer coefficient depending on the liquids, the hot steam and the cold steam. Here we have similar situation. We don't want to discuss this one in this course, but if you want to determine the efficiency, you can do that by going back to some of the correlations that are available in the literature to determine the efficiency. But the main point here I'm trying to mention is that the efficiency is not 100%. It's just assumption. Okay. Is this clear, guys? Okay, so I think I will give you. I think I will stop here. Since this is, we don't want to go through this little bit complicated stuff here. Not complicated, but requires some refreshment, and we have to postpone this discussion until inshallah next week. So we see you inshallah on Monday. Yes, at 8 o'clock inshallah. Is there any questions? Thanks all, guys. Have a good weekend. Enjoy the rest of this day and the rest of the week. Thank you very much.